So if you have questions during the lecture, or write it on the chat, or just speak, and I'll try to communicate with Professor Kareljan. Okay, please.
So good morning and welcome back, everybody. So I'm resuming my little story about quantum many-body physics and quantum computing and the various connections between these two things. Just to be sure, let me advertise once again these notes that I put out after each lecture. So there's a summary, there's some references, and there's some problems. So please, try those problems. They're not too difficult, I think, and you will know you only learn a subject by doing it and by going through some exercises. And again, or via email if you wish to help you along. So last week I spent quite a bit of time on general things about quantum computing and implementations via qubits that represent as spin and a half. So we looked at various Hamiltonians that we can use to to control these qubits and to send them in all kinds of directions that we want them to be. I also mentioned quantum simulation as a slightly different activity, but which is a very promising approach to addressing, let's say, our quantum many-body challenges. Actually, today most of my time will be devoted to quantum simulation, and then tomorrow and on Wednesday I'll be going full steam for the quantum computing side. But let me start today. So after the spin qubits Rydberg atoms as very nice platform to do computing or simulation. And one thing I haven't done is to actually explain how you can use a Rydberg atom system as an actual qubit. So let me start with that for today. So that will be a little story on Rydberg atom qubits. Last week we mostly talked about systems like this, right? We looked at two levels of some complicated atom, and we labeled them as G and R for ground state and Rydberg level. And we talked about how you can drive this atom from top to bottom using resonant fields. So you could say, well, here's our qubit, right? This is the perfect thing. Why not use this? So for example, well, the reason, this is not your perfect qubit, not at all. And this is because of the phases that are running around in a system like this. So for example, suppose, we think this is our qubit thing, and we prepare a superposition, let's say this one, right? The plus state on this qubit, and we let it sit for a bit. So we wait for a time t. So then what happens is that this thing will develop over time, time-dependent Schrödinger equation, and then up to a phase, it will actually end up at g plus e to the minus I t, and then a relative phase of, let's say, er minus eg times t, times the other state over square root of 2. And now what you see, so this delta energy, so this energy here, that's a huge energy scale, right? This is many electron volts, probably many tens of electron volts, meaning that this phase between g and r is running around like crazy. And it's probably impossible to keep track of that. And you have to do that, right? Because if you prepare, let's say, in the plus state, before you know it, this is a relative minus sign and you're in the minus state. And if this happens in a quantum circuit, all is lost. Then you've completely derailed the computation. So whatever you do, if a system has a bit of a split between the top and the bottom state, that's fine, but you have to be able to control that and correct for it when reading out your circuit. Another reason that the Rydberg states are not convenient, there's a qubit, so you need to trap atoms to be able to have them act as a qubit, and trapping Rydberg states is much more tricky than trapping ground state situations. So as a qubit, this whole thing is not a good choice. Now, I already mentioned last week what the better choice is. So there you take a Rydberg ground state, at least two degenerate states, or almost degenerate states. So what you do is you go for a situation with, let's say, something like this. So there's again a high excited state called R, but now there's two states downstairs, G1 and G2. And you typically, for example, using Zeeman splitting, that there is a bit of a splitting between these two energy levels. Let's call that small delta. But that's going to be way less than the splitting between G and R. So this can be slow relative phase can control in the qubit system. And now, so the idea is that G1, G2, so G1 call that 0, and G2 call that 1. So this is, a better choice for a Rydberg qubit. So the Rydberg state is out of it, but it's going to be used as an intermediate, to arrange for the gates that we need. Okay, so let's see how we could operate on a qubit like this here. So first, the 1 qubit gate. So to have those, that's relatively easy. So this is in atomic physics. People know how to drive between these kind of atomic levels. So what you typically use is some intermediate, let's say, auxiliary level. Call it F or so, which is not a Rydberg level, but some relatively low-lying level. And then what you can do, you make resonant couplings from G1 to F and from F to G2. So this is something called a Lambda system, right? So this thing has the shape of the capital lambda. So there's one level here, one level there, one level there. And if you carefully drive with these two laser fields, you can steer the system to move from G1 to G2 in make these 1 qubit gates. And that's a relatively easy thing to do. So I can give those a check. The more tricky thing is to do the 2 qubit gates. And last week I tried to convince you that all it takes to be universal for quantum computing is to make the C0 as a 2 qubit gate, and then you can compile whatever else you like to have into that. So the big question is, how can we arrange a C0 gate between two of these Rydberg atom qubits? So now there's a way to do that, which is actually not that difficult. There's various versions. I'll give you, I guess, the simplest one to follow, which is a 5-pulse protocol. So there's to do a C0 gate, I'll give you the 5-pulse version. You can be a bit quicker, but let me do it this way for today. So what is the plan? So okay, so the levels that we have, there's going to be atoms 1 and 2, so there will be these two states for atom 1, and then there's the Rydberg number 1, and then there will be 0 for the second atom, and also the R2, right? So this is the available states, and in terms of energies, they all look a bit like this here. So the two G's are down, 0 and 1, and the Rydberg is up. So now what can we do? So the protocol is the following. Step 1, we do a pi pulse, which is resonant on, let's say, the transition of 0 for atom 1 to the Rydberg level for atom 1. So if you wish, I'm going to tune my laser to this energy difference, which is different to the other one, right? G1, G2 are split, so I can be resonant with, let's say, 0 goes to R, but not 1 goes to R. So that's what I do. And pi pulse means that I wait exactly the right amount of time, so to lift the 0 to the 1 and then stop. Okay? That's the first thing. Then I do a bunch of pulses on my second atom. Again, 3 pi pulses. The first is going to be resonant between 0, 2 and R2. So that's, again, tuning the frequency just right to achieve this. The second is going to be resonant between 1, 2 and R2. And the third is going to be resonant between 0, 2 and R2 again. Yep, and then final thing is I do another pi pulse 0, 1 with R1. So I undo the first thing by the third step. Okay, so that's my proposal, and now let's make the truth table for this procedure and see what it gives us. Right, so let me make some room here for a truth table. So what we can have, there's 4 states that are of interest, so there can be 0, 1, 0, 2. There can be 0, 1, 1, 2, 1, 1, 0, 2, and 1, 1, 1, 2. So those are the 4 states that my 2-qubit gate is working on. The Rydbergs are spectators, they're not in the quantum register. Now let's follow, for example, the first state as we go. So in step 1, this is going to be lifted to R1, 0, 2. Because I'm resonant with that. Okay, and now you see pulse 2, 3, 4, they are all trying to do a resonant excitation of the second atom, by precisely tuned laser frequencies. However, as we heard last week, there's this Rydberg blockade business. So these atoms are, in each other's Rydberg radius, they're close, and that means that as soon as number 1 is in the Rydberg state, it offsets the energy levels, or it detunes, so to say, the second atom. So all these pulses are completely off-resonant and nothing happens. Okay? So by putting number 1 in the R state, it completely blocks what we try to do to number 2. So nothing happens here. And in the end, number 1 is brought back to its ground state, and so we're down to 0, 1, 0, 2. So that's the end of the story for that state. And now I guess you get the picture, right? The same story holds for the second situation. We go to R1, 1, 2, nothing happens, and we go back to 0, 1, 1, 2. But now comes the third situation. Now we start with atom 1 in the 1 state, which means the first pulse is off-resonant, so nothing happens there. So this state is unchanged, so it's still, 1, 1, 0, 2. And now, pulse 2, 3, 4 are going to be, so in this case, what happens is that in this step, 0, 2 goes to R2, so now I'm at 1, 1, R2. And then in the number 3 pulse, the Rydberg 2 goes down to 1, 2. So now I go to 1, 1, 1, 2. And then in this pulse, nothing happens, because that's resonant with the 0, 2, which is not populated. So now I go straight on, and then my first atom is brought down again, so I go to 1, 1, 1, 2. And now, final thing, if I start with this here, there's no Rydberg on the first, so this is inert. Now nothing happens here, but things do happen down here. So now this is 1, 1 going to 0, 2. Sorry, to R2. This pulse does that, and this brings it down to 0, 2. 0, 2, yeah. 1, 1, 0, 2. So I'm down to 1, 1, 0, 2. Okay? So that's a bit of bookkeeping, but you see what happened. I precisely achieved my C0 gate. Right? If the first, so it's a C0 with the control on the first qubit. If that's 0, nothing happens. If that's 1, it flips the second qubit. So you see that's check. We've done that with 5 well-tuned, well resonant pulses. You can do this, and it's a very elegant way of exploiting this Rydberg blockade business to do a non-trivial gate. So, there's actually quicker ways. For example, rather than doing these pi pulses, you can simultaneously drive the 2 transitions. So from 0 to R2 and 1 to R2, and then if you play this right, you get the a little bit quicker. But the idea is the same. So I give you the simplest scheme. Okay, so in principle, this is it, right? So if you can trap a bunch of Rydberg atoms, which people do with optical tweezers, and you can do the 1-qubit gates, and then if you like 2-qubit gates, you have to make sure your 2 qubits are within each other's Rydberg blockade radius, which is an issue with geometry. But if they are, you can play this game. And for example, last week I told you about Toffoli gates, and that those are a bit difficult. And in some cases, this Rydberg atom business is actually easy for that. For example, suppose you have 3 atoms like this, and the Rydberg radius for the first one would be, let's say, big enough like this, and for the third one, big enough like this. Then you can see you can kind of block number 2 from 2 sides. So you can make a Toffoli gate with not too much trouble. So this platform has this option of easy access to multi-qubit gates. So yeah, this is all a promising thing. Just one more thing I mentioned last week. So some atoms we like to produce, like strontium, they actually come with G1, G2, G3 up to G10 because of the nuclear spin of that particular ground state manifold. So there's also this variation of Q-DID systems that you can work with. Okay. There's some companies that are building quantum computers using this scheme, right? There's a thing called Pascal with a Q in France. There's a company called Atom Computing in Berkeley, and they're building these machines based on these principles. And what I hear is that they're making beautiful progress in controlling this. So my next topic is quantum simulation with Rydberg atoms. And I have a bunch of stories about, sorry, yes, question? Yes. So the question is, how many of these qubits? I think they do hundreds by now.
Okay.
Yeah, so it's not so hard to scale up. And you can actually, I think, like these Pascal people, they arranged atoms in the shape of the Eiffel Tower, because there's these tweezers and you can put them wherever you like and you can make nice pictures. So yeah, I think so that's relatively easy. The decoherence is extremely good because these atoms are all alone in vacuum and they don't decohere much. Of course, the challenge I think for this architecture is the gate, for example, the gate speed. These things are rather slow. Sometimes you lose qubits. Sometimes atoms escape from their trap and they're gone. So every qubit platform has its own challenges, and it's very interesting to compare and do these things. But for now, I gave you the basic principle, and I hope you appreciate that.
Sorry, Kareljan, can you repeat where did you put the material of your lectures?
Sorry?
The material of your lectures.
Yes.
Lecture notes, where they are, because...
I gave them to Filippo Colombo, and I think on the program, you can click behind my name and my lecture, and then I think he also put them in the same place where the Sachtev book is, this kind of hidden directory.
Well, apparently not, but okay, we will check
then
later.
I'll check with Filippo. So actually, after this lecture, I'll give him number 3, and then it should all be there.
Okay. So,
I'm told it's on the GGI webpage if you search a bit.
Okay, so
I'll check after the lecture. So let's do quantum simulation. So I'll call that QSim for today.
So we have another question. Sorry. For what was the second excited state F in the picture? So you had state
yes.
F.
It was to do the 1 qubit gate actually. So to connect, let's say G1, G2, I need a third state. So I bounce G1 to some auxiliary state and then down again to G2. And if I use my Rydberg, then I start to interfere with neighboring atoms. So for 1 qubit gates, I don't want that. So I use some other level that's easily accessible. And then it all depends, these atomic physicists, they know exactly where to look for, well-defined sharp transitions that can do this job.
Okay, thank you.
Okay, so for today, quantum simulation, QSIM, with Rydberg atoms. And I'll have 3 or 4 stories to tell you, which I think are all interesting by the right. Some of them, I report on experiments that were done. Some of them, it's like proposals from the theory side for what could be done. And I think it's all quite nice. So last week I distinguished 3 regimes of this of interacting Rydberg atoms: blockade, facilitation, dressing. And these simulation situations are they employ these different scenarios. So the first one I'm actually going to do, so give that a 1, that will be using the blockade regime. Yep, so I'm reporting from a paper of the Lukin group. Lukin group, if I may, he's the last author of these papers. And this thing was published in 2017 in a Nature paper. It's the famous 51 atom chain, you may have heard about it. So what these people did, they arranged 51 Rydberg atoms in a linear configuration like this. Open boundary conditions. They took 87 rubidium, and they made a certain choice for the G and the R level. So this is back to a single G. It's not a qubit situation, it's a situation with a G and an R, and the dynamics of these things. And now, so as we discussed before, everything hinges on how you arrange these various parameters. So there's this interaction between nearest neighbor Rydbergs, there's the next nearest neighbor interaction, there's the detuning, and there's this driving strength, right? And your choice of how you align these energies determines what kind of behavior you're looking at. And now the regime for this experiment that I'm discussing here is that the V, let's see, the V next nearest neighbor is the dominant scale, so it's way bigger than delta, which is way bigger than omega, and everybody is way bigger than V n n n. So this you can do, the V goes like 1 r to the 6, so there's a huge gap between n and n, and so you can arrange to be in this regime here. And this means, there's a complete blockade between nearest neighbor atoms. No way they can both be driven to the R state. And, if I leave it like this, everything's off resonant. But this here will actually change. So if you, what these people did, so they went to this regime and they adiabatically brought in their atoms and they looked what happened. And what is, I think, quite clear, you see because of this here, this dominant value of V and N, you can forget about having R next to R. But now let's say if we take delta so delta is like a chemical potential, right? It gives an energy to R versus G. And you can arrange that it favors, let's say, the Rydberg level. Okay? And if you do that, you try to make as many R's as you can, but you avoid next neighbor's R's. What you get is quite obvious. You get a state looking like RG, RG, etc. So they call this the Z2 state, or if you wish, it's a Néel state, antiferromagnetic state. So this is a state that can, by driving their system carefully, they can achieve that. So they look at this kind of crystalline state that's induced by these interactions. Yeah, so that you can do. And what you can do in the next step is then quench delta all the way down to 0 suddenly. So delta down to 0 means you're going on resonance, right? So I'm referring to what I said last week. So that we keep the driving term there. So there's this omega over 2, sum over all the sides of the, let's say, the X operator. That we keep. We starting from this state, we leave out any of the detuning, And the interactions are still in place, you know, the V terms forbidding nearest neighbor occupation and then being very weak for the rest. So this is what they observed. And I think this was kind of, you know, completely open experiment. Let's let dynamics see what happens. And then what happened was a surprising thing. So one thing they checked is what you can call the revival dynamics. So, you know, if you start from this Z2 state at t equals 0, and, you know, you let it evolve to some time t, and then, you know, you can check if you're back to that Z2 state, yes or no. So there's a revival situation. These things typically don't happen on you in quantum systems unless, you know, they're really small size. But the surprising thing in this system was the amplitude for these revivals were surprisingly large. And if I think I quote from the paper, they said, you know, the initial crystal repeatedly revives with a period that is slower by a factor of 1.38 compared to the Rabi oscillations for a non-interacting atom. Right? So there's a funny thing. If you do, you know, a term like this on a single atom with nobody around, you know, you get a Rabi oscillation, nice and clean. And the frequency of that is like 1 over omega. So it's set by this omega, and that's it. But now what they saw here is that there is this kind of revival dynamics of this Z2 state, a bit like this, where there is a typical period which is, you know, a bit slower than this Rabi oscillation in vacuum, so to say, by some crazy factor, which I think is 1.38. It's an experimental observation, and, you know, which was completely unaccounted for. Nobody saw that coming. So there was, you know, remarkable dynamics coming out of this experiment with, at that moment, no explanation. So this paper simply reported this finding, and there was, you know, no story for why that is. So I guess after that, the theory came. So this is a nice situation. The experiment was first. And they started analyzing, you know, this very simple situation in the end here. And so what they wrote in the end was, you know, let's say a model Hamiltonian, which is now known as PXP, which is pretty much this. So it's, you know, let's say we keep the omega over 2, and then we do the sum of all the sides, and then we do xi, precisely as here, and then, you know, I put a p and a p, where the p is the projector on the space that avoids these RR occupations. So, you know, I could write that differently, but that's what it is. So this is the Rydberg projector. And, you know, because this is what the model does, right? So again, so this term we keep. There's no detuning because we're on resonance, and the interaction terms we account for by a p forbidding nearest neighbor occupation, and, you know, no energy for the next nearest neighbors. So this is a very nice theoretical model that should account for the situation. It's deceivingly simple, you know, it's just a flip, right? X is just trying to flip. And the only complication, if there was no p's here, this is a trivial model. But these p's, it's a bit unclear. So it's a constrained Hilbert space. And it turns out that somehow these constraints are really important, and they give, you know, this remarkable dynamics. So what was found, I mean, there's a long story. The eigenstates of this dynamical system, there's a bunch of remarkable ones that go under the name of QMBS, quantum many body scars. So this is a scar, like you know, a scar on your body if you're injured. So, and there's a whole story. So, you know, I could spend two, 3 lectures explaining exactly what was done here. So the terminology refers to certain things known in classical dynamics, for example, chaotic billiards, where most states are random, but a few are nicely periodic and localized in space. Some of that survives quantization, and that gives you quantum scars, and in the many-body context, that's quantum many-body scars. So the story is there are special eigenstates of this Hamiltonian with very low entanglement, with a relatively high overlap these C2 states, these quantum many-body scars, if you draw them in energy space, they're kind of equidistant. And if you inspect what that equidistance actually is, it has this 1.38 factor. So obviously, if this bunch of states is dominating the Z2 state dynamics, this energy spacing is reflected in some kind of repetition time of the pattern, and that's exactly what happens. So there's this finding that this quantum many-body scar state spectrum looks like this with some spacing, and that is what is seen in the experiment. So this is quite a beautiful thing. So it's a new type of dynamics. So there's this whole field now of trying to understand quantum many-body scars, and it really came to us by an experiment that wasn't designed to do this. That was simply designed to see what happens if we do this Rydberg chain business. Yeah, so I think that's a very beautiful story. Another example where I keep my heading because I'm still going to be in the Blockade regime is a different experiment by the same group actually. But a different setup, and this is their dimer model simulation. So same group, the looking group, but much more recent. So I think the preprint was April 21, it's less than a year ago, I think, and the paper is in Science, I think. What they did here is they went to a 2D situation, which is a Kagome lattice, which is hard to draw on the blackboard, but let me try. It's a bit like this, and then this is roughly how the Kagome lattice looks like. So what they did in this experiment, they took a bunch of Rydberg atoms in the Blockade regime. Actually, I think there were 219 to be precise. And they positioned them on the edges of a Kagome lattice here. So let me give you the name. This is Kagome. I think Kagome is without capital and without accent, I learned. It looks like this. Kagome lattice. So the atoms are here. And so they took a patch of this geometry, which contains these 219 atoms. So that's what they did. And as you've learned by now, if you do the Rydberg blockade situation, the all important thing is how do you choose that radius, right? So, for example, imagine I've a Rydberg excitation on this location here. So who am I blocking with that? And that's a matter of playing with how large you take this Rydberg radius, which you can do because it has this omega in there, which we can play with as an interaction strength. And now the choice these people make is that each atom actually blocks 6 of its neighbors, which are the closest nearby. So this is blocked, 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 and this is blocked. So meaning that the radius they picked is precisely such that it blocks these guys and not everybody else. Now you can probably see why they did that. If you now make a configuration, a double R, so to say, within the radius, you can view that as a dimer or dimer configuration. Because if you imagine, now let me take red block, I hope that shows on the video. So this occupied, suppose this guy is in the R state, I can say, well, there's like a dimer situation here. And whatever other dimers I can put, they will not be overlapping, right, as a dimer covering should be. So for example, I've not blocked this position, so this could be another R, but that's okay because that would mean there would be a dimer like here, and it would be non-overlapping. There could be a dimer over here, there could be a dimer over here, etc. So I'm sure if the blockade business works properly, that I'm going to look at a configuration that I can actually visualize as a dimer state. I said dimer covering, that was a bit too quick. I'm not guaranteed that it's kind of fully packed, but I can hope for that. And that's what these people did. So they played with, I guess, their delta to favor as many readbooks as they could, given the constraint from the blockade. And the hope they had was that this way they generate dimer configuration lattice, which they were expecting to be, forming some interesting state of matter, some quantum spin liquid. And so, having done this, so they prepared states like this, and then they measured. So they measured where the R's and the G's were to be found, and they repeated, lots of times to get statistics. And then they kept track of two operators. So one operator they measured was, let's say, a Z operator loop. And they took lots of those. So yeah, maybe let me try to go into a bit of detail there, but not too much. So what you do is you draw a loop, going around some of the vertices. And then you do a Z operator every time you cross a line where there is a Rydberg or a G state sitting there, and you count, let's say, the minus signs of doing that. And as you can see, if there's actually a fully covered situation, then every vertex is touched by at least by a dimer, and that means that the Z operator loop is actually equal to a minus sign times the number of vertices that you enclose by doing this. For example, if my loop is over here, you see I would have 3 pluses and minus where I go through the okay, because so you can do this. So you can measure these Z operators by simply checking if it's a G or if it's an R, and then see if this thing holds yes or no. And what they found is that they can arrange all their parameters such that this is much happening, right? So the Z operator loops do follow the -1 to the number of vertex, which indicates that indeed, they were looking at approximate dimer coverings. So that's nice because that's what they set out to do. Second type of measurements which they report are X operator loops. So you make similar loops like this, or maybe bigger ones, and you look at the X operator. Now, what does X do? X flips from G to R, right? That's the X operator. So there's the R and there's the G. And the X is the flip. So if this thing has a non-zero expectation value, it means that the configurations are somehow oscillating between a G and an R, right? If they would be completely nailed that it's always the same thing, you would find 0 for that X operator. But they find non-zero values, which means that they're looking at an oscillating state. Every time you measure, something different comes out, so there is coherent superpositions. So this, the fact that they do establish non-zero values here means that there's actually, again, there's coherent superpositions in these states. And and this is a hallmark feature of, let's say, a spin liquid or a quantum liquid that you're looking at. And because of the way this is all set up, you're actually looking, and that's their claim, at a topological spin liquid. Topological quantum spin liquid. For example, some of you may have heard about the toric code, which is sort of the proverbial quantum spin liquid. This thing is rather similar. So with these two observations made, you've established that you find yourself in a state of this dimer system, which is very similar to, let's say, low energy state, ground state of the toric code. So that's quite remarkable. These superpositions, they happen for loops that are rather big. If you look in the geometrical size, this is sort of long-range coherence. And that all happens in this quantum simulation. So that's nice. It's nice because, we like to understand these spin liquids, and we don't have too many examples coming to us, from what nature makes. It's also nice, so that's at second arrow, because, people have proposed to use topological code or comparable systems with topological order, as actually a protected quantum register. So there's, I haven't said much about that, but there's the need to have some kind of fault tolerance in quantum computing, and one way to get that is to use topological schemes. So if a thing like this can be, improved and perfected, it could actually be like a first step in, building hardware for protected quantum information processing, also known as fault-tolerant quantum computing. So I think, both these things are extremely interesting. We're learning some new physics, and we're making a step towards, let me write it, protected quantum information processing, QIP. So I think, beautiful stuff, and a very nice demonstration of what quantum simulation can do for you. I think maybe this is a nice moment to break. Is that okay? It's a bit early, but it makes sense in terms of where I am.
Okay, if you...
Maybe questions before the break?
Questions? I have one curiosity. So in this scheme, the experiment with the lattice, they can have a way to access the topological entanglement entropy of that state. This leading calculated by Kitaev skill.
Yeah, so the question is if you can, let's say, measure this topological entanglement entropy, so you can split in two pieces and trying to access
fluctuation of, I don't know, in the ground state, or, well, in fact, in that state.
I'm not sure, because local measurements will not do, but maybe if you measure enough of these loop variables, you can get your hands on that. It's a nice question.
Okay, no, well, because it seems very interesting if you say that it's a...
Yeah. So Nigel, maybe I'm coming into your story, or, okay.
Okay, here in the chat, well, if you have questions, write it in the chat. You can also write it in the break, and I will read it after when we resume. Okay, so we can stop here probably for 10 minutes, no?
Yeah, good.
And then we come back, well, let's say at 10 minutes to 11. There will be 8 minutes.
Okay, next example, this facilitation regime. I brought that up last week in the case of two interacting Rydbergs, and I proposed to look at this, to look at the detuning equal to minus VNN, so the nearest neighbor interaction between two Rydbergs. We looked at n equal to 2, so 2 atoms, and then we observed, the GG state is offset as compared to the other three, so GR, RG, and RR. So all these sit at energy equal to delta, and this is energy equal to 0. So clearly the trick of tuning this delta equals minus VNN is that this RR state, which does have the VNN but also has an extra delta, is degenerate, right? So that's the n equals 2 situation. Let's imagine, following, again, some experiments that were done to do a chain of n atoms in this regime and see what happens there. Let's do n equal to 4, okay? And let's, play the same game we do over there. So just let me be extremely explicit. You'll see there is going to be a degenerate, well, there's a bunch of degenerate manifolds. Let me draw one of them. So if I look, for example, at everybody in the R state, that is degenerate. There's a whole bunch of things. For example, I can do G, R, 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 G, G, R, R, or G, 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 R. I can also do G, and then I can start eating away R's like this. R, and I get G, R, G, G, or I can do R, G, G, G. So exercise, that this triangle of states is actually degenerate under these conditions. There's clearly a pattern, which is that I can look at clusters of R's, right? And as you see in all these configurations, there's one cluster. It can be 1 R up to 4 R's. It can be placed in various places, but there's only one of them. And if I try, for example, RG, RG, it will be more energy. So I have and my offset doesn't work anymore. So what you get, so there's this, this number n cluster, which is the number of R clusters. I drew you the n cluster equals 1 situation for n equal to 4. So in general, that's 1/2 n times n minus 1 states. And you can play the same game for n cluster equals whatever you like. And then the general thing you find is that, let's say your Hilbert space, this is a Hilbert space graph, if you wish. It looks like a truncated hypercube of dimension d equals 2n classical, n cluster, sorry. So that's not so hard to see, right? If suppose there's 2 clusters in the middle of lots of G's, then you can flip a G into an R on either side of the cluster, and so the cluster controls 2 dimensions to some kind of Hilbert space. So in general, you get this truncated hypercube. But it's kind of interesting. You can always make a Hamiltonian that connects states via hopping and interactions. You can always draw a graph of Hilbert space, and you say, here are my states, and you draw lines to connect them, and you get this big mess of some graph with lots of connections that are to. In this case, the mess is extremely small because it's like here it's just simply a square, with a truncation over the diagonal, and more generally, it's a hypercube. And now, now the funny thing is that, so the dynamics of this, you see the active term dynamics is again the x, right? So it's again omega over 2 sum of xi. So it can flip G into R, and that way, for example, if you do that to this state here, you can connect to this, to that, to this, or to that. And you're actually moving on a very simple geometry for your many-body dynamics. Okay? Now you see the funny thing, because you can also do one-body dynamics, you can do one-body classical dynamics in the same geometry. So you make a billiard, which you give this shape, and you can look at, classical trajectories of particles in that billiard. And you can compare those to the quantum dynamics. This is, and there have to be similarities because of sort of obvious reasons. And now, believe it or not, if you look at the classical dynamics of a billiard of this type, this is supposed to be 45-degree angle. You'll see lots of, depending on details obviously, but you see lots of not so structured orbits, but you also see some very special ones. For example, if I start a motion right here under 90 degrees, my particle goes here, it goes here, it goes here, and then it goes back again. So I get nice orbitals, which go 2 directions. Now this here, these are like classical scars of the classical dynamics in this kind of funny billiard. And if you prepare a wave packet on this quantum Hilbert space that sort of starts here and that moves in this direction, it will show some similar behavior. So you get another notion of quantum many-body scars, quantum many-body scar states, but in this case with a very explicit connection to classical dynamics in some billiard setting. So that's quite interesting. So this was, observed experimentally. So this thing was built experimentally and tuned to this facilitation condition, and certain things were seen. And actually, I was involved in a study with Gilles Minar and Bart van Voordem, my collaborators, where we looked at these scars and to what extent they actually happen and they're visible. So the story is a bit complicated. This thing is so simple; it's integral. And so that kind of system, the scar dynamics isn't what you expect to happen there. There's other things to take over. There's too many conserved quantities for this to be interesting. But if you add disorder, that goes away, and you're much closer to this one particle scar situation. And we actually found on paper, if you take the system in the presence of some disorder, which actually you always have if you build it as an experiment, these quantum many-body scars are enhanced and they become much more visible in the sense that you can take pictures of the quantum dynamics of this type here, and you see these scars if the disorder is added, is increased. So that's quite an interesting thing by itself. And again, it's quantum dynamics, but since the Hilbert space is so structured and so simple, you have easy access to certain things which are usually out of reach. Okay, so it's a little, if you wish, a short intermezzo to my third example. So the last one for today is yet another proposal for quantum simulation with Rydberg. It's done in the lab. I hope it will be done soon. But it's a theorist's proposal, and it employs this last regime where we use Rydberg dressing rather than actual population of the Rydberg level. So now this needs a bit of introduction, this story. So I have the following setting in mind. I'm going to look at a one-dimensional situation, but now, again, my previous examples were, atoms nailed in a quantum chain, and degree of freedom being the flips R2G, 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 right? And we talked about that. So the last example looked like motion, but that was, coming from flipping R2G, R2G, etc. But now I want a situation where I have actual particles that can move. Okay, so what I want is, let's say, spinless particles. I'm thinking fermions, but in 1D open boundary conditions, it's there's no essential difference with boson fermions. So I do 1D lattice, so a chain if you wish. Then what I have in mind is a constraint, which is that there will be no nearest neighbor occupation of my particles. So if you wish, I'm going to assume a P, a projector, very similar to PXP situation, but now not for game, but for, let's say, itinerant particles. Now, the third thing is that I'm going to assume a tuning, and I'll come to why that is, of, so my VNNN. So if you wish, the no N and N occupation, you could say what that really means is that my VNN is essentially infinite, right? It's so high that it completely destroys any chance of having that situation. But my VNNN, I want to be, okay, and I'm going to tune that to be equal to J, which is the hopping strength of my particles. So my particles live on a chain and they hop with strength J, amplitude J. And I'm going to, again, I want no NN occupation, VNN equals infinite, but I do want an next near neighbor repulsion, with strengths v and n, and I'm going to tune that to be equal to j. Now, why on earth would I do this? So there's a funny result. If I do all this, the resulting model is supersymmetric. So it comes out of the blue like here, but so the result, claim, theorem, whatever, this model with all that put into place, it has, you know, supersymmetry. If you wish, it's n equal to 2 supersymmetry. If you wish, it's space-time supersymmetry. So, you know, there's something confusing between this kind of supersymmetry, which involves space-time symmetries, such as the Hamiltonian, and sort of graded Lie algebra symmetries. So people say there's a supersymmetric TJ model. That you know, kind of supersymmetry. What I have in mind is actual supersymmetry, the same way, you know, particle physicists consider it. And again, the claim is that this model has that. And, you know, it's completely unclear from here, but let me try to give you that, result. This actually goes back to a paper I did with Fendley, Paul Fendley, Jan de Boer, and myself back in 2003. So this is like old stuff. Let me give you how this is. It's easy to actually establish this. So suppose, you know, we have our setting given over here. We describe these particles with canonical operators. So, you know, there's Ci's and C dagger J's, and they anti-commute to delta ij. So that's my notation. I think you all know how that goes. So if I have that, I can start writing operators on my system. Let me write the following operators. A thing I call Q, sum over all the sides, Ci, and then let's say Pi. So it's an operator that tries to extract a particle from the system using the C in all positions, and then there's a vector that's going to, so this P, which is necessary to make sure I'm staying in my constrained space all the time. In particular, if I do Q dagger, so the conjugate, that's the sum over all the sides of C dagger I, Pi. And now obviously, if I try to add a particle, I have to better be careful with the P. So my P in this case, to be completely explicit, so the Pi would be, you know, 1 minus Ni minus 1 times 1 minus Ni plus 1. So, you know, Ni, you know what that is. It's C dagger I, Ci. So that counts if there's a particle, yes or no, on the side I. And so this Pi, you know, it checks if the left neighbor is empty and the right neighbor is empty. As soon as there's a particle, it kills the state and you're out of the space, right? So this Q dagger, it checks if there's room for an extra particle, and if so, it puts it there. Okay? So that's just a definition. It's all extremely simple, but now I can do a bit of algebra. And the algebra is only 5 lines, but it tells you everything you want about the supersymmetry. So first result, Q squared is equal to 0. Q dagger squared is equal to 0. So these are nilpotent operators. And that's, you know, because I'm building them from fermions, and the fact that P's are interfering doesn't affect this. This is still valid. Second result, and now that's a definition really, I can define a Hamiltonian to be the anti-commutator of Q with Q dagger. That's a natural thing to do. So if you wish, this is my space-time supersymmetry version of, you know, the that people write who do particle physics 10 dimensions or so. Yeah, and now the thing is, if this is my definition, you know, as a consequence, by some almost trivial math, I can prove that H, Q is 0 as a commutator, and H, Q dagger is 0 as a commutator. And so now comes the terminology. These Q's I call supercharges. And what my construction shows, if I define H like this, it commutes with the supercharges, so it is supersymmetric. Okay, very general observation. This is with n equal to supersymmetric quantum mechanics, so to say. This is in any quantum mechanical system. As soon as you find two of these Qs, or one Q and its dagger, you can do this, and you can play the game. Okay, and now, I guess the claim is if I do this construction for that choice of Q, I get this answer. This is precisely what comes out then. And that's why this system is supersymmetric in that sense. So, can you see how that goes, or should I say a bit more? So maybe, maybe the surprise is that there's hopping, right, in this Hamiltonian, because the way I define it, it's a bit almost like PXP. I tell you there's an operator that puts a particle or takes a particle out, and I commute them, and then suddenly I have hopping. So let me maybe illustrate how that goes, why that is. So suppose, I have a configuration, there's...
excuse me?
Go,
I have
please.
a question. So n equals 2 here means there are two supercharges, Q and Q dagger. Is that correct?
Yes, that's it. So
okay,
if you wish, it's a complex supercharge, so it's not equal to its conjugate. So there is a version of this algebra where the Q is like real, and that's what people call n equal to 1 supersymmetry. But my thing is n equal to 2, definitely. Okay, so my little demonstration of why that structure equals that Hamiltonian, and in particular for the hopping. So suppose, I have my situation and I have, so let's say, I have empty side, particle, empty side, empty side. And I'm going to act with this H. So let's see what we can do, first Q and then Q dagger. So let's do that, Q dagger. So on this state. So what Q does, it tries to make 0, 0, 0, 0, and Q dagger tries to put back a particle, and it can do that in 5 places. So this is actually, a sum of 5 terms, 1, 0, 0, 0, plus this, plus this, plus this, plus this. Okay, so that's what Q dagger Q does. Now let's do Q dagger. So what Q dagger tries to do is add a particle. But there's 2 forbidden places that are next door to the particle already there. So what it can do is and now let's be careful about signs, it can do this. It can make 1, 0, 1, 0, 0 by using the creation operator on side 1, or it can have a particle in the end, but then there's a minus sign because I jump over a particle. So I have a minus this, the 1, 0, 1. That's it. And then I should still do the Q, right? I've done Q dagger, still have to do the Q. So Q tries to take out a particle. Okay. So there we go. It can take out the first guy here, and that gives me 0, 0, 1, 0, 0. And that can also happen here. So this guy gets a weight of 2, actually. And then it can also take this particle over here, and that gives me minus 1, 0, 0, 0, 0. Or it can take out the particle in the middle over there, which gives me minus 0, 0, 0, 0, 1. Okay, so I'm just doing this. Do this just to be very explicit. So now I have to add these 2 things, and you see the terms that have particles far from where I started cancel. So, for example, this guy cancels against this guy, and this also goes like here, because I put a particle. Well, both operations give me the same thing with a minus sign. Right. So then there is the thing with the term in the middle. So I'm left with, if I do the final answer, this is my scratch paper final answer. I think I get 3 times this 0, 0, 1, 0, 0. So there's some chemical potential, if you wish. Yeah, I think that's right. And then I get, 1 time 0, 1, 0, 0, 0, and I get 1 time 0, 0, 0, 1, 0. So now I've accounted for this one, for this one, for this one, and for this one, yeah. And so you see what happens. Again, there's some chemical potential, which is, a constant term in there. And this is the hopped situation. So you see there's a hopping with J equal to unity in this case. And so, what you can also check with a bit of algebra is that there is this V and an N with the same unit strength if you do all this. A fun thing. So somehow we have, spinless fermions on a chain with some not too crazy in dynamics. So there's hopping and there's some repulsion, and then there's a P constraint. And the claim is that the whole thing, constitutes a supersymmetric model. Maybe let me leave that and let me remove this. So let me give you a few facts. So this thing we call the M1 model, because after we went on and we defined an MK model. So let me give you a few facts about this M1 SUSY model, so to say. First of all, it's integrable. So it's really nice. It has everything you can dream of. It's integrable. It's critical. In the sense of a 1D quantum chain critical. Yeah. And now if you say, well, wait a moment, if it's 1D, it's critical, we know where that leads. We have field theory formalism for dealing with critical 1D systems. They're called conformal field theories. So there has to be, seeing this criticality, there has to be a CFT at work here. But since the whole thing is manifestly supersymmetric, and then also in the field theory limit, it has to be a superconformal field theory, an SCFT, and it has to be of the n equal to 2 type, because we have 2 supersymmetries and they both stay. So this has to be an n equals 2 supersymmetric field theory. Now there's a list of those. You may have seen there's a what are called n equal to 2 SCFT. I think this was first analyzed in the context of string theory. When I was a PhD student, this was the vogue of the day. And people found minimal models, so to say, of superconformal field theory looking like this. So they come with central charges CK equal to 3K over K plus 2. Same sequence that you know from the SU2 models, K equals 1, etc. And so now what happens, and that's why this thing is called the M1 model, it turns out we hit the K to 1 point of this series. So it's the smallest n equal to superconformal field theory on the planet. That's what this system actually makes. So our M1 model is the K equal to 1 minimum model of n equal to superconformal field theory. So that's really nice. Once you have this idea, you can simply check it. If you do a bit of numerics, you can extract central charge and dimensions in the usual way, and it all fits extremely nice. So actually, I feel good about this. This school is called statistical field theory, and I think I didn't bring up too much field theory until now, but now I do. So I hope I'm with the target subject of the school. So it is really nice. There's much more. So this model was studied off and on by myself and then Fentley and other colleagues, and we learned lots of things. For example, we this thing a version which we call the MK model, also on a chain, which is more or less by construction made such that it hits the number K minimal field theory. So we have all of them in the list, so to say. We also looked at putting this same M1 model. You see the definition here. You can put on any graph that you like. If you give me a bunch of vertices and you tell me who's connected to who, so this exclusion business, I can put this thing on any graph and I can see what happens. So for example, I did a student project not too long ago where I asked the student, put this thing on the platonic solids and tell me what happens, and then you can do that and you can learn stuff. And I wanted to surprise this when we did this. If you put this M1 model, so let me write that here. So the M1 model on 2D grids, or lattices if you wish. For example, Kagome, one we saw before the break, or 2D square, or 2D triangle, or whatever. What you typically find, you see, I didn't say that, maybe I should say that right here, in my algebra section. So, you know, what this Hamiltonian, by definition, you know, it's positive. The way it's defined, every possible eigenvalue is always positive. But there can be states, you know, there can be states psi that are annihilated by Q and by Q dagger. There can be such state, or there can be no such states. But if this happens, you know, if a psi has these two properties, and the Hamiltonian kills it, because all the Q's kill it. So this would be a state with H psi equals 0. And this is what's called a SUSY ground state. Right, so it's a ground state because it sits at the lowest possible energy. And it's supersymmetric because, you know, it's a singlet. The algebra cannot change the state at all. So excited states typically come in doublets. So there's one state, and then you do Q, you get another state, and Q dagger, you go back to the first state. Here, these states are all alone, and they are the supersymmetric ground states. And there's this interesting question, do you have such states? And if so, how many do you have? For example, the M1 model, you know, depending a bit on details, but on let's say, well-chosen geometry, it has 2 ground states. Not 1, but 2. So for the experts, there's a thing called the width index, which allows you to track that number. The width index for M1 model is 2. And the width index for the first, so the width index for this here is k plus 1, if you wish. So the first model has width index 2, and that matches with my lattice model. But now, you know, let's go to 2D grids and look at that number. So the number of ground states. So let's do a grid with some kind of lattice structure. Let's give it size, you know, m times n or so. So for example, this could be my Kagome situation, or some other lattice that you prefer. And so, you know, let's count the ground state number as a function of n and n. What you typically find that number ground states, SUSY ground states, is some lambda to the power m times n, where lambda, you know, is strictly greater than 1. Which is very strange. So what you find, you know, if you make tables, that's how we started discovering this. We made tables of this width index for, you know, a Kagome patch or a square lattice patch, and then we found, you know, numbers that were increasing quite rapidly, and then we did more study and systematics, and we found typically these numbers are actually, you know, growing extensively, meaning, you know, as an exponent in the number of lattice sites, m times n, which is a very crazy thing. So this we call superfiltration. So it's frustration in the sense that there's exact degeneracy of quantum ground states, and it's super because it comes from supersymmetry, and it's super big. So, so this is, you know, a feature of this M1 model. And one of the reasons we keep studying these things is to understand, for example, can we figure what lambda is? For the triangle LEDs, there's a lambda. We know it by numerics. We don't know it by analytics. It's somehow a very difficult problem. There's a few examples where we picked a funny lattice where we know the number. In many cases, we don't. So this is quite a rich field of study still. But in one day, we know everything. So, you know, it's so special, integrable, supersymmetric, critical, and, you know, we know very well what we're looking at. Okay, so now this was, you know, all theory play, and during all these years, I sort of had in the back of my head, can we find a physical system that actually...
I have a question, Kareljan, sorry.
Just a second. So can we have a physical system that actually realizes this model, and can we look at it this way? And what will come as a proposal for that? Okay, but the question, yeah?
This supersymmetric model is, well, as you also said, it's very similar to this PXP, no? In a way. But there are scars here in the dynamics.
A very good question. We looked at that. So it seems like there's a lot of analogy with the PXP situation. I think there are no scars in the model as such because it's integrable. So it's somehow that doesn't go together very well. I think what's open is if you change the model a bit to break applicability, but keep the supersymmetry, which you can do. That could be scarce. It's open. It would be very nice to check that. So again, the plan, and that's for the rest of the day, what I'd like to talk about briefly. Can we set up a quantum simulation to actually have this model in the lab and study it? So we have a proposal for that. This came out in Physiograph Letters like last week or so. So it's all on paper. It's not been done. We think it's doable, but we're not sure how difficult it is. Well, we know it's quite difficult, but we hope it's doable. But let's see. So let's try to do the QSim of the M1 model. Let's start in one dimension. But clearly, we have in the back of our mind, if we can do that, then we can maybe address this 2D situation as well and learn new things, right? Which we have trouble finding from other treatments. Okay, so now having heard about the Rydberg block business, I guess you will think, and that's also what I first thought, it makes perfect sense to try to represent these fermionic particles as Rydberg states of some Rydberg atom, right? Then the blockade is built in, and that's for free. However, I don't think that will ever work. Rydberg states are not that stable. If you start them off, they'll decay. They're hard to trap in optical lattices, and there's quite a few reasons why this is probably not going to be the solution. So the proposal we have is to use Rydberg atoms, but in this dressed regime. So again, so the idea is to use Rydberg atoms, but to represent the particles carrying the model by let's say the G state and not the R state. But to use the R state to induce interactions that are of the type needed for having this model. So and the concrete numbers we worked out in our paper is actually to take 6 lithium and a certain Rydberg excited level, which seems to have all the numbers quite about right for doing this. And again, so you use this and you induce interactions via the R level. Now, actually, I told you how this goes last week. And what I gave you in the end was some kind of graph, like so, where there was distance here. And there was W of R over here. So the induced interaction strength in this Rydberg regime. And there was a curve that I derived, which is, I guess it's also in the notes and the exercises, which is about like this. Right, so there's the van der Waals tail, the one for R to the 6, but then there is this flat top behavior at shorter distances. So this is what we can, achieve using this dressing business. So the idea is, we have an optical lattice situation to represent our 1D chain. We trap these atoms in their ground state G. There is, a hopping possible because of this, you can put the particles so close that they have a certain amplitude to hop to the other side with strength J. And then we irradiate the particles with this resonant, well, not resonant, off resonant, driving towards the Rydberg level with some detuning that induces this W of R. Okay, so that's what we imagine doing. And now you see, on this R scale, there's a certain spacing here, which is, let's say, R0, my lattice spacing. So there's, on my R axis, there's 1 R0, there's 2 R0, there's 3 R0, etc. So what I have, if I have this potential, there's the strength happening to me at 1 R0 here, this 2 R0 here, and 3 R0 here. Now, remember what I want from my model. First of all, I want exclusion of nearest neighbors. That was on this blackboard. I erased that. So this represents, V nearest neighbor, because R0 is nearest neighbor on my lattice. So what I would like this to be infinite, right? the thing over here is, you know, V, N, 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 I guess. So that's, you know, 3 sides away, next, 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 nearest neighbor. In my model, that's 0. Shouldn't be there. And then the one in the middle is you know, V, N, N, N. And this I'd like to be equal to J. So what I'd like to have is that my scales work out such that this thing here is actually J, and that this is actually way bigger, this is way smaller. And then I'm approximating my desired situation as good as I can. So, you know, this is the plan. Obviously, it will not be perfect. And, you know, the fact that more than a year passed between our preprint and our PRL publication was that the referee was insisting that this is not good enough. So we actually proposed, you know, ways to improve this. For example, if you do a double dressing, so if you use 2 R's, you can double dress the level and you can tune much better. And we believe if we do that, you know, it's almost perfect and it should be to go. But in any case, you know, this is the reality of a non-perfect implementation.
We don't see what you just wrote.
Sorry, the red is not coming over. Let me repeat it in white, sorry.
Thanks.
Yeah, it's important, right? So because this potential is all it has. So the hopping is sort of a standard thing we can establish hopping particles in an optical lattice. So all that matters is to get the interactions right. And what we need, so this is position R0, that's the nearest neighbor couplings. And they should be, you know, infinitely strong. The second cross is the next nearest neighbor coupling. And it should be equal to J. That's, you know, if I break that, I break the supersymmetry and everything stops. And then the tail should be absent. So these are V, N, etc. And they should be 0 to have my model perfectly there. And again, I think in practice what you can achieve is that maybe there's a factor of about 10 or so between this one here and the one on top. And I guess like 1/10 to the one down there. And yeah, we should see if that's good enough to not completely mess up, you know, the proposed signal that we have for this supersymmetry. So this is the plan to build a thing like this. But now suppose we do that. So how do you tell the supersymmetry? Suppose, you know, we can build the optical lattice, the potential, we put some particles, and now, so how do we tell that there is this supersymmetry? That was a bit of a puzzle because, you know, you can propose certain measurements, but they don't necessarily reveal supersymmetry. For example, if you would, you know, realize the ground state, that would be nice. You know, zero energy state, you could maybe check this energy, but you don't see supersymmetry in front of your eyes. So we thought a bit about what we can propose there, and for that, a bit of theory again. So back to this M1 model, let's do, you know, periodic boundary conditions, and let's give our lattice length 3 times some number. In that case, as I already mentioned, there are 2 zero energy ground states. So that's nice. If you look carefully, you'll discover the particle numbers, let's call that F, maybe fermion number, is actually equal to L for both of them, you know, which is 1/3 of the system size. So these ground states are 1/3 filled. So the maximal filling of the system is half, because, you know, you can alternate particles and empty sites, but the energy is lowest for these 1/3 filled configurations. And there's 2 of them. So that's nice. Now if you go to other length of this system, or you this thing open, make open boundary conditions, you don't see all these ground states. So in particular, if you go to open boundary conditions, you know, which is the experimental step for sure, and you give the thing length 3L+1, you'll discover there are no zero energy ground states. So the Whitney index is actually 0. Somehow the finite size is important, and you lose those ground states. They don't happen. So for example, you know, if you take if you take the conformal field theory limit by making the thing big, you'll see certain conformal modules realized, but they will not be the vacuum models, what you say. There'll be some excited levels. So that's a fact, but actually this is a good thing because our proposal is to precisely focus on the situation with 3L+1 sites. Because if you look at what happens there, typically it's like this. So L equals 3L+1, open boundary conditions. Here's my chain, and left and right. What you typically see, and there's ways to establish that, is that the low configurations for this system look like this. So they start off in the first ground state. They end up in the second ground state. So these two ground states that I have here, I could label them 1 and 2. So there are certain local patterns of particle empty side, etc., that you can recognize also in open chain geometry. So typically this is what you have, and then there is, a domain wall, if you wish, a kink. So there's, somewhere in the middle, let's say location I can put a kink that connects these two vacua. So, we have certain tricks of studying this. We deform a bit Hamiltonian where this picture becomes much clearer, and then we extrapolate back to the conformal point, and we see it still happens this way. So, in a sense, the lowest lying excitations are these kink states, and there's a whole band of them. So, there's a band with a certain dispersion that we actually know in closed form. So, there's a band of these kink states, and there's a certain dispersion. And we know all that. It's actually quite interesting exercise that we could do. But now you see if this is a state, and this kink state would actually have particle number F equals L. Now I told you there are no supersymmetric ground states in this system. So if I do a supersymmetry on this K, I will get something new. And it turns out if I do a Q dagger on my kink, I get a new situation, which I call skink. This is following particle physics people who put an S in front of leptons to get sleptons and all that. So the superpartner of kink we call skink. It has one particle extra because that's what supersymmetry does. If I have K bar, I can go back upstairs using Q to make K again. So we have a little, what's called a supersymmetric doublet of two different states, having different particle number, but having identical properties. So in particular, this band and this dispersion is identical between the two because supersymmetry maps you from one to the other. And supersymmetry is like a K equal to 0 operator, so it doesn't affect the dispersion at all. So that's what you have. And this actually allowed us to make a proposal for, an experiment detecting supersymmetry, so to say. So what we propose is the following protocol. Step 1, you prepare these kink states, and let's say, with index I all the way to the left. So you try to make a kink that's, let's say, glued to the left of the system, to the left boundary. So let me call that K left. That's a state with L particles. And you also prepare K bar left. That's a state with L+1 particles. They're different states. The left hand. And then you wait, right? So you have this interaction on. You say initial state kink on the left, and then you simply sit back and wait. And what you do is you monitor. You monitor some observables, some things you can get your hands on, like occupation numbers of the sites all the way to the right of the system. So this is the right, and this is the left. So that you can sort of spot the arrival, so to say, of the kinks and the anti-kinks, the skinks, so not anti-kink, but super kink, at the right hand of the system. So I guess mathematically what you do, there's this initial state K left, which you time evolve using Schrödinger equation, and then you overlap with K right. and you take the absolute value squared, and that's the thing O of t. So overlap after time t. Yeah, and you do this for kink and you do this for super kink. Okay, and so this is an interesting quantity. Yeah, let me maybe use this board. So you can compute how that looks like if it has, some structure that you can expect, and it does. You see, you can kind of sketch this thing, I think, with some physics intuition. So first of all, there is a velocity in the game. It's a conformal field theory point, so there is like a Fermi velocity, a v sub f. And so the travel time of these kinks will be roughly, the speed will be roughly v of f. So if you look in the time domain, which is my t in this formula, there's a special point when there's kind of L over Vf. So that's like the travel time to cross the system once, and then there's twice that, and there's 3 times that. So, and if you compute this thing here, since we know the dispersion of our kink states, we can actually do this with some saddle point approximations. You can get that really almost closed form. So obviously what happens, in the beginning nothing happens because the kink is on its way, right? So initially nothing happens. At some point you get a signal slightly before L over Vf, and you get a peak. The peak sits somewhere here. So there's a nice formula that explains this, but this is roughly how it looks. And this goes on, the peak dies out again. And then something else happens at the 3 L over Vf point. And so somebody can see why that is? Why at that time? So, if I make a movie, so 0 kink sits at the left, and then after time L over Vf, it has traveled all the way to the right. But then, since there's an open end, it bounces back. It travels to the left, bounces back, travels to the right. So after 3 times L over Vf, the front of the kink has gone, this way, back, and this way again. So the front starts interfering with the tail. So you get funny oscillations. And indeed, that's kind of a beautiful thing to do. If you analyze this signal, so right at 3 L over Vf, you get something like this, and then it keeps going. So there's a very characteristic expected signal. I mean, this is how it looks in the large L limit. If you do 10 sides, it doesn't look as nice as this, but you can still recognize this structure well enough. Now comes the point, since kinks and skinks have identical dispersion, everything is identical. So the proposal we do is, do this experiment, kink on the left, go to the right, monitor the arrival, make the curve for the k. Second experiment, prepare a k bar, a skink on the left, go to the right, monitor the arrival time, and make a picture. And the prediction is, because of supersymmetry, these things are going to be identical. Okay? And so our proposal is, try to do these things and try to establish 2 identical curves, expressing that you're looking at, a super doublet, so to say, of supersymmetry. And again, we think that with all the numbers, we try to be reasonable, and we think it can be done this way. And we propose, and again, I'm hoping that I come back here for another school. I can actually report on an experiment that did this and saw this. So yeah, that's the story for this final proposal for quantum simulating with Rydberg atoms. So I hope you've appreciated, I think in these 2 hours I had like 4 completely different physical setups. Chain, a Kagame lattice, another chain, and now this crazy thing. In all cases, it seems these atomic simulators are good enough to actually display some of the real physics happening there. And so I think that's quite beautiful. And that's on top of the very first thing of today, which is to use these atoms simply as a digital qubit and build a computer working on this principle. And the story for today. Any questions?
So yeah, you mentioned the field theory of your SUSY model, but what kind of field theory it is, like some free boson, free fermions, or sigma models in string theory, or so what kind of a continuum field theory it looks like?
Yeah, so there's a question on, so how this conformal field theory that represents this M1 model in the scaling limit. So let's say the M1 model SCFT. That's an interesting story. So the obvious way to actually build
So
to build n equal to 2. Sorry. So I guess you can build, if you take a complex scalar field phi and a complex fermion psi, that's free fields. There's a natural way n equals 2 supersymmetry, something like, simply the product of these two operators would give you a supercurrent and a super symmetric situation. This, if you look at this is like C equals, well, 2 for the complex boson and 1 for the complex fermion. This is C equals 3. And if you wish, this is like the k goes to infinity limit of the minimal series. I give you the minimal series was Ck equals 3k over k plus 2. And if you wish, the k goes to infinity limit is the free particle representation using complex psi. Now these minimal that is below 3, and the model that I need has only C equal to unity. So my k equals 1 model, C equal to unity, that I can build using a real, so this was a complex field, using a real scalar field. So this I learned from a paper by Watterson, which was a famous paper in early CFT days. So he understood this. So he took a free boson thing. So you write the standard, let's say, C equal to free boson theory, and you understand that e to the, let's see, I squared of 3 phi vertex operator, that would have h equal to 3/2. And I can also do the minus thereof. So these would be 2 supercurrents in that notation. So in that free boson model, I have 2 supercurrents, and you can check that these actually nicely make the OPEs for n equals 2 super conformal symmetry, and also the commutator algebra is realized. So with this, these are the supercurrents, and then the fermion U1 current, so to say, is like d phi, and then as you know, the stress tensor can be expressed in the phi, and that's it. So that way you can make this model in the easiest way. So this comes from Watterson, probably 1984 or so. It's very early on, very short after PC.
Good. Okay, so other questions?
Maybe I have a question regarding the model itself. Just wondering, so I mean, you were talking about integrability and then with the periodic and open boundary condition. So, but usually for integrable models, you might expect to have some other kind of integrable boundary conditions. Is this kind of known, or can we learn something from the field theory about this?
Okay, so the question is about open chain boundary conditions, if they tell me new things. I think for the M1 model, not much happens there. So you simply, have an open end and that's it. For the MK models, which I didn't spell out, but that are a bit more complicated, there are such boundary conditions, and there's actually very beautiful interpretations of these things as spin fields for parafermions and stuff like that. But since maybe that's the way to say it, the M1 model has this only the scalar field active for the CFT. That doesn't leave room for such kind of boundary fields, I think.
Okay, thanks.
Other questions? So I have one here. When you plot in this plot, no, of this return amplitude, O, I guess you call it, no?
Yeah. So O of t,
Yeah.
like the.
So
Right.
this curve is obtained, at least some part of it is obtained with the CFT, or is I mean, just a lattice or numerics?
No, it's not a CFT. So it's two things. So we got our hands on the dispersion of these kink excitations, which is not a standard result in CFT, not at all. We're still studying exactly how to understand that, but we're pretty sure we nailed that. And then a saddle point method.
Okay. Thank you. Okay, so if, well, also in the chat I don't see other questions, so I think we can stop here and thank Kareljan for the lecture. Okay, so see you later.